and I did my presentation on the Stirling engine and the Stirling cycle. Little introduction, I'll be breaking down the Stirling engine with the Stirling cycle. It's a simple engine that uses thermodynamic principles from the Stirling cycle to convert heat into mechanical work. It was never a widespread thing, so it's not very well known, I guess. It was never very effective in lots of applications. Some history. So Robert Stirling, that guy right there, he got a patent in 1816 for the first ever closed cycle hot air engine. It was meant to be a competitor to steam engines, that's what he thought. In his patent, he described how it could be used for furnaces for like iron smelting and glass. In 1827, him and his brother James got a second patent, which their design was inverted, and they also added a compressed air pump, which increased the air pressure, giving it higher efficiency. And in 1840, a third patent was filed, which led to the invention of the Dundee engine, which was used by the Dundee Foundry Company. In 1845, James Stirling gave a presentation on the third patent to the Institution of Civil Engineers, claiming the Stirling engine wasn't only just to save fuel, but it was also a lot safer than steam engines, because steam engine cylinders would consistently blow up and kill people or hurt people, and also would just cost a lot of money. So those claims were true. It was safer and it did save fuel, but it wasn't efficient, meaning whenever it was used at high temperatures, the cylinders would consistently fail. So much so that the Dundee Foundry Company, which I mentioned before, eventually even replaced all their Stirling engines with steam engines because they just kept facing cylinder failures. These engines were manufactured until 1922. They were mainly just used to pump water and generate electricity, but they still never reached widespread use anywhere. So the theory, this diagram does it's simple, but it does a good job explaining it. The wire mesh right there is really where the regenerator is in the system, and it collects heat as the heat comes in, and then it uses it again over to keep the cycle going. But so you have an external heat source, it heats the cylinder, it moves the pistons, which generates pressure in there, and it goes along. I'll get to that in a second now. But it's a closed cycle system, so they have a set amount of fuel and it stays in there the whole time, and you don't refuel it or anything like that, and you can't get it out either. It's also reversible, so it can be used as a heat pump, which I'll get to as well. And the change in pressure in the gas is what allows the whole engine to create work. So in a two-cylinder engine, your first cylinder will be heated by something outside of it, as opposed to like a gas engine, which is an internal combustion engine. These aren't, and there's actually no combustion going on. I mean, unless your heat source is a fire, but it's on the outside. And the other cylinder will be cooled by an external cooling source to lower the pressure. The presence of the regenerator in the engine is why it's a lot more efficient than any other hot air engines from before. And, here are equations for the heat in, the heat out, the net work, and the efficiency. The Stirling cycle, it's got two isothermal processes and two isochoric processes, as you can see. And so the isothermal expansion, the energy from the external heat source increases the internal temperature, increases the pressure moving the first piston. Then isochoric heat removal, the piston pushes heated gas into the second cylinder through the regenerator, and that's where the regenerator collects heat from that gas. And then in the second cylinder, it's cooled, allowing it to continue to be compressed. The third step is isothermal compression. The gas is compressed in a space which is maintained at a low temperature, and then the gas releases heat to cold sink, which is just where it escapes. And then the isochoric heat addition is the fourth step. Second piston moves up, forces the compressed gas back into the heated cylinder, and then it is reheated where the cycle just starts all over again. So, research. It's an external heat, it needs an external heat source to operate. So as opposed to like a gas engine, the heat takes too long to get to the cylinder, which is why it's not efficient to use for like cars, because you need it to like go like that with an internal combustion engine for your car to operate effectively, and to change the output, when you press the gas, your car accelerates right away, and it just wouldn't work with this because it takes too long for the heat to get to the cylinders. It wasn't useful for all these things, that's why it never got widespread use, but it still gets the attention of researchers because it's interesting due to it's quiet, because there's no combustion. The fuel, you don't have to refill it. You could use many different types of gas for it. It's low pollution, high efficiency, and it's got high power density. And like I said before, it's also reversible, which is also what the Philips company here used to its advantage. From 1938 to the 50s, it took interest in it and it licensed multiple patents on technology. One thing they did was design a generator with the engine as the drive, but they also used their research to develop cryogenic cooling systems using a reverse Stirling engine concept like a heat pump. Said the heat pump. It's also, so the Stirling cycle is very similar to the Carnot cycle, except the two isentropic processes in the Carnot cycle are just replaced with isochoric processes in this cycle. It also has the same maximum efficiency of the ideal Carnot cycle. It's also similar to the Ericsson cycle, and Ericsson is the person who not invented the Brayton cycle, but it was named after him. And then the Ericsson cycle is also, well, there's two cycles named after him. He invented the first cycle, which is the Brayton cycle, and then the second one, which is typically the same thing, just it's got higher efficiency, and it is has an infinite amount of heating and intercooling stages. But this one is also two isothermal processes, but instead of two isochoric processes, isobaric processes. And that's my references.